we talked about what forces are and what they do, right? We talked about Newton's laws 1 and 2. And we're really, remember I said we're contracting forces in kinematics a little bit this year. So we're just doing these 4 to get started. We're just doing gravitational, and that means weight. We did weight. And we're doing normal. We did normal to death on Tuesday. So today we're doing friction and tension forces, okay? So hopefully you got these down, and now we're going to do friction and tension. And then these are just things you do with all of them. We talked about this some already. Force components is from last week. You know how to take components. Free body diagrams, we did a little. And net force is for solving kinematics. We'll do a little bit of that. I think we did some of that. And today we'll end with a little bit of Newton's third law and action-reaction pairs. All right? And then we'll be done with forces. So if you're doing the reading, you can see how it sort of is scattered among 3 chapters in this book. But that's so the book can lay it out very clear, if you like things laid out very clearly. Okay? All right, so let's see. So we're going to start with friction. This is our next force in our little tour of forces here. Okay, so friction is a force. Spoiler alert, that opposes sliding motion. Notice I didn't say it opposes motion. I said it opposes sliding motion. And we'll talk about why I said it that way. Or the pent-up desire for motion. It depends on the situation. To solve problems, you have to understand pent-up desire. It acts along or parallel to surfaces. All right, so the normal force is pretty obvious which way the normal force acted, normal to the surface. That's why it's called the normal force. Perpendicular means normal. This one, the name doesn't give it away, but from your intuition, you may be aware that it is along the surface that you get it. Okay? So we're going to do, there's 2 kinds to keep up with. The first is static friction. So the 2 friction forces are very similar. One applies to things that are static, and one applies to things that are sliding. Okay, so static friction, the symbol we use is F, little f with an S, with a vector hat on it, because all forces are vectors, as you know. And it's F between surfaces that are not sliding. Surfaces that are not sliding. And of course, that's what static means, okay? Now, notice I'm not saying moving. If you say this a little less thoughtfully, you might say it must be things that are not moving if they're static, but it's really referring to the 2 surfaces against each other. Right now, there's a static friction force between this block and this block. Okay? And if I slide this, now they're moving. But it's still a static friction force, isn't it? Right? Because these 2 aren't moving with respect to each other. Okay? We could do a definition in terms of moving reference frames and all that stuff. It's more fun just to say sliding. Okay? Between the block and the table is no longer static. That's sliding. But here I can accelerate the top block with static friction. Wow, static friction can cause motion. Okay? So just because it's static refers to sliding of the 2 surfaces that you're calculating it for. Okay? Let's talk about, let's do the block on a plane. Here we go. So we're going to say, let's tilt a ramp up like this, right, at angle theta, and think about a block sitting on the ramp like that. So we can do that here. I've got all my blocks today. Here we go. So there's a ramp, and here is a block sitting on the ramp, and it's being held in place by static friction. And I know you can't see it because everything up here is brown, but maybe there's a little bit of contrast, and it's not camouflaged completely. So if we were to think about the forces on this block now, we would say, okay, well, we know mg is down that way. That's always the case, and I drew it sort of at the center of mass because that's where it acts. We talked about last time there's a normal force pushing it up, right, that. Pushing it up, and last time we did some calculations and we figured out that the normal force is equal to the component of gravity this way, and the other component of gravity just slides it down the block, or slides the block down the ramp. But it's not now, is it? There is a component of gravity pulling the block down the ramp, but it's not going down the ramp because of friction. There's also a force right here. This is a static friction force, keeping it from going down the ramp. Okay, that's why it's not sliding. If we're going to do a free body diagram, which of course we do, I highly recommend, we just think of the mass as a single little point. It's got mg down. It's got a normal force normal to the surface. I'm not trying to get the magnitudes right here. That normal force is a little big. And it's got Fs back, static friction back. So if you were going to break it into components and do a problem, you'd probably rather draw it like that. Right? Okay, so that's that. So now let's talk about how to define this friction force. Well, we just drew it. It followed the rules I said. It's along the direction of the surface, and it's opposing the pent-up desire for motion. It's back. Right? Which way does this want to slide? It wants to slide this way. It's this way. It's kind of easy to tell in this example. It wants to slide down. Friction pulls it up. Sometimes examples get hard to tell. Like, which way is the static friction on a tire when your car is speeding along, but it's not actually sliding against the road? That's hard to tell, right? So the way you figure it out is in your mind, you slowly turn off the friction and say, which way does it go? That's the direction of pent-up motion, okay? If you slowly turn the friction off of a tire, it would start to spin too fast. So friction actually pushes the other way. So the static friction force on a tire is actually forward. That's why the car goes forward. But here it's a little easier to see. If it wants to fall this way, the friction force has to be that way. But let's talk about the magnitude, okay? So now, what is the magnitude of static friction? Oh, no, it's not an equation, or it's not an equal sign. It's a less than or equal to sign. Less than or equal to mu s times the magnitude of the normal force. Right? Because it's always about two surfaces, so there's always a normal force to think about. So as long as you have a normal force, you have some static friction. And but then what is that? Didn't tell you the value. Right? That just said it's less than some value. So really the answer is whatever value needed, whatever it takes to avoid motion. But there's a limit from 0 newtons to, and then the maximum is the static friction coefficient times the normal force. Okay? So I mean this mathematically clearly, you know, this means less than mu s times n, less than or equal to. It could only go down to 0. It can't be negative. Right? You never have a case where the friction force pushes it forward. If you figure out how to do that, just let me know, because we'll be really rich. Okay? But it can't really happen. So it's from 0 to mu s times the magnitude of the normal force. Okay? So it's just some value. It's sort of like it's a constant, but it's not really a constant. It's a value that changes up to a constant. Okay? So let's define, you know what the normal force is, you know what that force is. Let's define mu s is the coefficient of static friction. Of static friction. Let's talk about some properties of it. It's unitless. You can tell by looking at that equation. This is in newtons, this is in newtons. It's unitless. It's usually roughly a half. Okay? Order of magnitude, it's a half. Okay? It can't be below 0, or you would have, that'd be like a frictionless surface, it's 0. As soon as you have any friction, it starts to go up. It can be larger than 1. There's sort of a myth out there that, it can't be larger than 1 because something about conservation of energy or whatever. Well, ask a gecko. It can be larger than 1, okay? So it's just usually most typical surfaces rubbing against each other. The static friction is about half the normal force on the surface, okay? But you'll do problems where we say it's 0.1, where it's 0.9, where it's 0.05. So when I say it's half, it's like usually 0.5 plus or minus 0.45. Okay, so it ranges kind of between 0 and 1. All right, so now let's think about, are we sure really, though, that it could take different values here? So let's go back at let's think about that it can take different values. Forget the ramp. We'll do the ramp in a minute. Like what is the static friction force right now? It is actually 0, okay? To go sideways is 0. Why is it 0? Because it's whatever value is needed to avoid motion. So what value is needed right now to avoid motion sideways? You all do this. I do this. 0. Okay? It doesn't need any motion to avoid any force to avoid motion sideways because no force is being applied sideways, right? But if I push it now with my finger, I'm really pushing it. It's not moving, right? Now there's a static friction force that way. Is it equal to mu s times the normal force? No, it's less because I'm barely pushing it, right? It takes any value it needs to keep it from moving. But what's the highest it can go? Mu s times the normal force. What if I push harder than that? Oh, there it goes. Okay, it moved. Okay, so if it's not pushing, it's 0, bigger, 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 mu s times m. Right? And then that's as high as it can go. So I can take that whole range of forces, whatever it takes to avoid motion. Okay? Right now it's 0. Right now it is not mu s times m. Okay? That's just the maximum it can be. We're going to think about that more because we're going to measure it. You can actually measure the static friction coefficient. Very exciting thing to do. You could even measure yours. You could sit on a ramp and tilt it bigger. I've never done it myself. You would think I would have that on my CV somewhere. Let's see. Okay. So let's measure static friction coefficient, because that'll force us to do some free body diagrams and etc. I guess I could have just written mu s. It's coefficient. Right, how do we measure it? So we're going to go back to our ramp situation here. So there's the ramp, like that. And let's say you can vary the angle. Okay, so let's assume that the ramp is at theta, but you can vary theta in principle. You could take the ramp, and this is what we're going to do, is we're just going to have this thing on here, and we're just going to say it's a tilt ramp, where I can sit here and go, oh, different thetas, different normal forces, different maximum friction forces, blah, blah, blah. So let's calculate some of those. Here we go. Okay, so here again, I'll just draw it real fast because we already drew it once. Here's the mass. I don't even draw vectors on that. We go straight to the free body diagram. mg, all right? The normal force, you know, has to be normal to that surface, N. And the friction, static friction, you know, has to be back. Fs, there it is. Let's see. So first, now let's think, what coordinate system do we want to work in? Do we want to work in x and y? No, because in x and y, you got to think about the components of this and the components of this, and mg is only in the y. You want to work in the coordinate system of the problem, right? So you want to work in, shoot, my m is in the way here. You want to work perpendicular to the surface and parallel to the surface. So you can think of it as I've tilted x and y. You can call it xy, x prime, y prime, whatever you want to call it. I like to actually use these symbols, parallel and perpendicular. Okay, so let's start perpendicular to ramp. The perpendicular direction, it's a Cartesian direction. You can write Newton's second law. Perpendicular, why not? Some of the forces in the perpendicular are equal to 0. It's equal to 0, not ma, because it can't possibly fall into the ramp, right? These are solid objects. Can't happen, all right? So we say it's equal to 0. And then we got to do this vector sum thing, right? So last time we went out of control and did every step and got the magnitude and the angle of each vector. Rather than just doing it intuitively, I am conflicted about what to do this time. Let's just go through each one and just see what we get here. Yeah, what the heck, let's do it. So for this vector, what is the component in this direction? It's the magnitude, n. Remember, if I write it without the vector hat, that just means the magnitude. Times the angle to get this component would be the sine of the angle from the x-axis, n times sine of 90. Okay, this is probably the last time we'll do it this explicit. Right? What is mg is straight down, mg. What angle is mg at? Oh, I thought I did this in detail. Oh, there it is. Let's see. Well, technically, with respect to this is 0. It's at, oh my God, 270 plus theta. Right? So I didn't write where the theta angle theta is. It's right here. Right? So we actually go all the way around 270 plus theta. So mg times the sine 270 plus theta. Right? And then the last one is the Fs. Right? So plus the magnitude of the static friction force times also the sine of 180 degrees equals 0. You're like, what is he doing? Let's go through the trig real quick. What's the sine of 90? Very good. Sine of 90 is 1. What is the sine of 270 plus theta? Oh, Google sine of 3 pi over 2 plus x is negative cosine. It is. Minus mg cosine theta. Go check it yourself. What's the sine of 180? 0. That was exciting. Plus 0 equals 0. So what if I did this the intuitive way? I would say, what is the component of this in the direction perpendicular? It's in. Right? What is the direction of this in the direction perpendicular? Well, there's one component. There's the other component. Cosine is adjacent. It's mg cosine theta. Oh, crap, it's backwards. So we'll put a negative sign on it. Okay? So this is how we usually do it. But if this was like magic to you and you don't know where this came from, it's coming from here. Okay? So we're not going to keep doing that. It takes too long. I mean, it's okay for you to do it on homeworks and everything. But in the lecture, I'll just start doing them intuitively. But if you ever don't see where it came from, we can always go back and do it that way. Just raise your hand. Hey, I want to see that one in excruciating detail. Jump around and make us say the trig stuff too. Okay, so now let's do parallel. Okay, so what we learned here is the magnitude of in terms of m and g and theta, right? So the normal force is just the component of the weight into the ramp. Right? And we did that before. We did that with normal force last time. But now we're going to do parallel to the ramp. Okay. And we're going to erase part of this really long equation because it's in the way. You saw it. You're with me on that one. Oh, sorry, I didn't have it on me. Oh, well, we can't go through all these. They're too long ago. We'll do the ones that say now. Can you go through how to find the angles? No. Never mind. Good. Wait. Why is f equals 0 perpendicular? This is the direction perpendicular to the ramp. The definition of the friction force is that it's parallel to the surface. So parallel is 90 degrees from perpendicular, so it has no component perpendicular. Right? Maybe that was the never mind. So you're doing good. Where did in sine theta equation come from? The one I just erased. We were doing the detailed conversion from polar to Cartesian. You'd have to go back to the first lecture to do it. So ask in office hours. I'll take you through it. Super careful. Okay. All right. Parallel to the ramp. Okay, let's see. Sum of the forces parallel equals what? Sum of the forces parallel equals 0 again. We're actually doing statics here. We're not letting it move. Right? Is this thing moving? No, not yet. So we're solving the static case. Sum of the forces parallel equals 0. So now we're going to do it the quick way. What's the component of the normal force down the ramp? 0. What's the component of mg sine theta down the ramp? Of mg down the ramp. It's mg sine theta. Right, this is mg sine theta. We call down positive. So mg sine theta. Sine theta. What's the component of the static friction force down the ramp? It's negative Fs. Okay, minus Fs equals 0. See, that could all be justified with detailed trig. And it will help some people and it will confuse others. Do we have a pledge problem soon? Good timing on that question. Excellent. Yes, we have a pledge problem soon. We don't know exactly when yet. We're still working on the details. A class is an organic living thing. We don't lay out the entire schedule on day one. We got complaints last year that they didn't have the date of every possible thing that could happen on day one. So a class is a living organism. Don't make me go on. Okay. So the friction force Fs. So what we're trying to solve here then is the friction force Fs. The static friction force is mg sine theta, right? That's the friction force holding that thing up. Now you say, wait a minute. I thought it was going to be, because you take so long to say things, I thought it was going to be mu times mg cosine theta, right? Because that's what this formula says. No, it doesn't. Is this an equal sign? No. The friction force will go from 0 to whatever you need to keep it from moving. So the friction force is not yet mu times mg cosine theta. Right now, it's only mg sine theta, right? It's getting there. It's getting higher and higher. Okay, so friction forces are not always equal to that. That's the limit. Remember, that is the limit. This is the alligator eating the big side. Is that how it goes? No, you didn't do that. Okay. You had to be from Florida, I think, to do that analogy. So what we're going to do now is we're going to measure, show that we can actually measure mu. Okay? So what we're going to do is raise theta until it slides. Okay? Raise theta until it slides. All right. Let's see. What is the fancy mu on the left chalkboard? That is the coefficient of static friction. This is the Greek letter for M, I think. I don't know. I don't know. I didn't take any classics. I believe that is the Greek M. Someone correct me. The subscript is S for static. We use mu a lot in physics. Okay. Okay. So what we're going to do now is say, what if we increase theta? Right. So here I said the friction force isn't mu times mg cosine theta. It's mg sine theta. But eventually, think about it. As sine gets bigger, as theta gets bigger, sine grows and cosine shrinks. Right. It's good to have sine and cosine in your head. Right. Sine is 0 at 0, and it grows with theta. Cosine is 1 at 0, and it shrinks. So as I raise this, the friction force we need is getting bigger. The friction force available to us is getting smaller. Right. Friction force we need, mg sine theta, is growing. Friction force that we can have, mg cosine theta, mu times mg cosine theta, is shrinking. So eventually those two are going to cross, right? And what's going to happen? There, it slides. What angle is that? Somebody measure it. 30 degrees, thank you. So it slid at right around 30 degrees, right? So raise until it slides. Let's see. So let's see what happened, right? So Fs needed grew because it went as sine theta. This means goes as. It's not actually an alpha. I think it's a symbol physicists made up. Okay, it's not a Greek alpha. It means proportional to. I don't know the history of that symbol. I apologize. And let's see, Fs you needed grew. The Fs available shrank or shrunk? I'm going to say shrank. Goes as cosine theta. Shrank, right? And eventually they cross, okay? So eventually you reach the point where this saying that this equals 0 is no longer true, right? So you lose it when mg sine theta equals mu s mg cosine theta, right? So this is the condition where it'll start to slide, where this basically can no longer be 0. Right? This will be greater than 0. So if you plug in, you would get that this has to be true. I've run out of board, and we can't spend all the whole day on this. So what does this mean? Oh, mg. It means that sine theta over cosine theta equals mu static. Right? And sine over cosine is tangent theta. Right? So what this means is if you want to find the coefficient of static friction, it's just the inverse tangent. Oh, I'm sorry. It's just the tangent of the angle. Is you measure the angle where it slides, and it's the tangent of that angle. Right? So here we go. It was sliding up, and it was about 30 degrees, and the tangent of 30 degrees is something. I forgot. I don't know. It's like a half or something. It's not a half. It's between 0 and 1. Right? It's 1 over the square root of 3, maybe? Possibly. I think it is. No. I don't know. Anyway, it's a number less than 1. And it wasn't even exactly 30. Whatever angle you get, you plug it in, and that tells you what the coefficient of static friction is. Okay? So you're like, yeah, maybe. Or you might be just full of crap, right? So let me prove it to you. Let's get two objects, one that is very high friction and one that is very low friction. Okay? So very high friction is my phone because it's in one of these cases that helps you not drop it, right? So it's rubbery. You don't want to drop your phone. And then this is the charger, which, as you know, is very slick because it's from Apple, right? So it's white and it's smooth. So which one do you think has a larger coefficient of static friction? The phone, right? So the charger has a smaller one, so it's going to go at a smaller angle than my phone, probably. There goes the charger, right? And then the phone, I mean, this is OtterBox level shit here, so I don't know if it's ever gonna go there. Oh, barely. It's vibrating too. Look at that. Right, so a much higher angle for the phone than the charger. So that helps your intuition and helps you believe in the demo. One first, and then the other. So if we wanted to, we could measure those angles and get mu s and turn it into an engineering project on them. Okay, so that's static friction. Now we got to do kinetic friction. All right, let's do it over here. So all that was about things not moving. All we did in terms of motion is we calculated the limit where something starts moving. We didn't actually calculate any values for something actually moving. Did we? No, we did not. When does static friction turn into kinetic friction? Right now in the lecture. At the 21st minute. 26th minute. Kinetic friction. It turns into kinetic friction when it starts moving, right? Is Fk, we use a little subscript k to mean kinetic, between two surfaces right? It's not the friction force of something moving. Something can move and not be feeling kinetic friction, like I showed you with the two blocks, right? It has to do with the sliding of an interface. The Fk is between two surfaces sliding against each other. Sliding against each other. I'm a few letters away from trouble here, okay. Okay, so now let's draw it first. And say here's a surface, right? And here is a block. And we're going to give the block an initial velocity, like that, right? So now two surfaces are sliding against each other. The block is sliding against the table. So you know what's going to happen, right? Initial velocity, and it stops. I gave it a velocity. The velocity slowed down. The velocity changed. There must have been acceleration. What caused acceleration? A force, right? So there was a kinetic friction force back here. Do these cancel? No. This is a cartoon. I drew velocity here just to give you the feeling of a velocity. I drew a force this way. When you're doing the cartoon, you have all kinds of different vectors. Don't get too intuitive about them canceling. These aren't going to cancel. This implies this one will get smaller, but don't get drawn into a drawing. I don't know. So a wheel experiences no friction rolling. Oh, it does. A wheel is a device that lowers the friction a lot. Okay, that's what a wheel does. I don't think we're going to do wheels too much. It's very confusing. What happens when the friction force equal to the coefficient of static friction, x, the normal, is it motionless at the exact moment? We'll talk about that in a minute. Okay, so here it is. Let's do the free body diagram of this thing just for fun. mg down, normal force up, and Fk to the left. The velocity is not a force, right? When you do a free body diagram, that's only for forces. You don't go drawing velocities and positions on it, right? So there's your FBD. And the magnitude of the kinetic friction, this is actually a lot easier because the magnitude, I'll put the bars to really stress, this is the magnitude, is simply equal to mu k times the magnitude of the normal force. Not less than or equal to, it's just equal to. So it's just a constant. You don't have to worry about, well, how fast is it going or whatever. No, it's just a constant. Now it only is there if the thing is sliding. But as long as it's sliding, constant force. Okay, and then mu k, as you can tell, if you're into symmetry, is the coefficient of kinetic friction. Right, and it's also usually about 0.5 plus or minus 0.45. Right? So it's between 0 and 1 usually. Right? 0 would be a frictionless surface. It can be as high, it can be above 1 in principle, but it's usually below 1. Okay? So the interesting question is what we're going to address next, which is, which one is bigger? It would seem like if they're equal, you'd have this problem right when you hit that force. Isn't that weird? And yes, you're right, it gets weird. Okay, so let's get it weird here. So this is something that sort of confused people for 2,000 years, right? So if force causes acceleration, what's going on here, right? Why can I push and get a constant? I'm pushing with my hand, I'm getting a constant velocity. I'm not accelerating. Well, it's because of friction, right? So let's go through just the numbers real quick. Or we could skip that and do more interesting things. Let's do that real quick. Okay, so let's apply a force. Apply a force and get constant velocity. And question mark exclamation point means we're confused, and I'll put Aristotle to make it clear that you're probably not confused about this. We're just going back in time before we knew about friction and say, how is it possible that I'm pushing it and it's going at a constant velocity? So we'll just go through the numbers real quick. All right. We'll do this one really fast. Here's my hand pushing it, right? It's going to go at V constant. Let's do a free body diagram to figure this out. Yes, excellent idea. Thank you. So here it is right here. And mg is pulling it down, right? Normal force is pushing it up. Yes. And now what I'm going to call is the push force, okay? You're only responsible for 4 forces: gravity, normal, tension, friction. But then when we push something, it's like a normal force. So occasionally we'll give you a new force where we just say there is a force applied. So don't panic if it's not one of your 4. For your hand, I usually just call it F push, right? F push forward. It is a normal force, basically. It's just like a normal force. It's normal to your finger when your finger presses against it. But just to be more clear, to not mix it up with the other normal forces, we call it F push. And since it's sliding, these two surfaces are sliding, there's a kinetic friction force between them. Right? So there's your free body diagram. It looks very balanced, right? So apply force, and the answer is yes, if, and let's see what has to happen in the y direction. The normal force magnitude just equals mg. That's boring. Sum of the forces in the y, we got normal up minus mg down equals 0. So the magnitude of the normal force is equal to the weight. Boom, there's no angles involved. But let's look to the right. Sum of the forces in the x. Sum of the forces in the x equals, in this case, also 0, right? Because constant velocity, right? We're moving at a constant velocity, so A is 0. Well, what are they? Well, it's the push force, which I can tell is moving to the right. If you want, you can multiply it times cosine of 0. And then there's the friction force, which I can tell is moving to the left, so I'll put a negative. If you want, you could say times the cosine of 180 to get the negative. It's that same thing we were doing. A equals 0. So the answer is you just have to push with the kinetic friction force, which you know, right? You'd have to push at mu kinetic friction times mg. Fk, we said by definition, is the kinetic friction coefficient times n, and n is mg. Right, so there's the whole thing. All right. So when I do that, when I push it at constant velocity, it's like I'm some sort of experimental genius that I can push it exactly. I'm calculating in my head mu k. Mu k is about 0.6. Okay, 0.6, and the weight is about... No, I'm just here intuitively. It's easy to push at constant velocity, especially if you were in marching band, right? Yes. All right. So another thing about that experiment that throws people off, we'll do more complicated problems in the second half, but let's just talk about some more basics real quick. Okay, yeah, this is just for fun, and then we'll stop. Yes, and this answers the question somebody asked, which is what's going on with the normal for, which one is bigger, right? And the question that you could ask is, this isn't just Aristotle, you might ask this, how do you get to V constant? You get to, so this will be a good review going back to kinematics graphs, right? It's not moving, I apply a constant force, and now it's going at a constant velocity, and I stop and it stops moving. Well, there had to be some acceleration. The force couldn't have been constant the whole time. So it's sort of like the trajectories. I say ignore the part where we throw it. Just think about when it's in the air. The same thing would be true in this problem. You'd be told something is being pushed and is already moving at a constant velocity. But sometimes people really want to know things, okay? Right? So it's good to think about this a little more carefully. And let's look at the history of the velocity here. It's actually kind of interesting. Time, velocity of this whole experiment, it was 0 for a while, and then I got it up to some constant, and we pushed it for a while, and then everything just stopped, because I stopped. So there's your velocity. It looks like that. Let's plot the acceleration under that. All right, what would the acceleration look like? Well, it's just sitting there at 0. Now the velocity increases, so that's like a spike in the acceleration. Oh, like that, like the girl on the trampoline. But then during this time, the acceleration is 0. The slope of this line is 0. dv dt is a, right? So there's no slope, no slope, no slope. And then you get a negative thing like that. For a little bit of time, there's a negative acceleration. So that would be there, right? Interesting. Let's put the force on here. Okay, so this is an axis of the force of push that I pushed with. I'm going to put labels on it that are equal to the values of the coefficient or of the static and kinetic friction. Okay, it's not a plot of static or kinetic friction. We're just going to put values like that on it. Okay? So what this would say is that here, what did I have to exceed? I must have exceeded the static friction force. I must have exceeded mu k or mu s mg cosine theta. There's not even cosine theta. I must have exceeded mu s mg, right, times the normal force. So I must have gotten all the way up to f, or a little f static, like the maximum value. So I must have pushed really hard like this and gotten up here. And then it starts to slide. And then it goes constant velocity. So the kinetic must be right there also, but it actually is always a little bit less, F kinetic. So I accelerated it, but then I went to a force that was equal to mu s times ng. So I actually come down a little bit, like that. Right? So the answer is the static friction coefficient is always a little bit bigger than the kinetic one, for the exact reason that you were thinking about. If they were equal, it'd be hard to define what happens right when you hit it. Does it move or not move? Well, it's always slightly bigger, so it takes a little bit of a push to get it going, and then to go at constant velocity, you pull back. And you almost feel like you can feel that if you push a block. Kind of to really push a block at constant velocity, you push it, and you can almost sense that you're pulling back to make it go constant velocity. It's really in your head, but it feels that way. What happens here? What force stops it? Kinetic friction stops it. Right? So what happens here is I stop pushing. I go to 0. If I stop pushing, is the total force on the block 0? Nope, it's still moving. Right? So I stop pushing here, but it still feels a kinetic friction force because it's still sliding, but it rapidly stops it. Right? The kinetic friction decelerates it and it stops. So actually why it starts and why it stops are different. Different forces. My push started it and kinetic friction stopped it. Okay? All right, so that's it for friction. I had one problem that was so trivial it would have been boring and you'd have fallen asleep. I'll do it on a video or something so you can fall asleep at your computer. So let's take our break and then we'll do tension. Okay, so we now have done weight, normal force, friction. So the last one that we care about is tension. Tension. T. Now this is going to be exciting. You're going to be happy about this. You ready? It's a scalar. A scalar, we're back to high school physics, algebra-based, yay! A scalar property of a string or rope or cable. I'm just going to call everything a rope, right? But you'll see problems, string, rope, cable, whatever you want. And it's in newtons. How can a scalar be in newtons? Well, a unit doesn't have a direction. A quantity has a direction. So a scalar can be in newtons. Now, here's the sad part. But we're going to talk about the tension force. And the distinction is actually important. The tension force, which is also T, but with a vector sign on it, okay, is the force a string or rope applies. The force a rope applies to an object. Right, to an object at the point of attachment. At the point of attachment. Right, yes. What is the magnitude of the tension force? It's equal to the tension. So the rope is under a tension of 10 newtons. Then if that rope is attached to something, it'll pull it at 10 newtons. Right, so T, it is both the scalar property of the string and it also, without the vector stuff on it, is also the magnitude of the force. It's both. Okay, so you can just think of it as a force. It's fine. Just wanted to get a little specific. Technically, you got to realize it's really a property, scalar property. Let's see. The direction of this force is along the string or the rope. Whatever direction the rope is pulling at, that's the direction of the force. So you just draw a little force along the rope, and you put a T with a vector sign on it, and you're off to the races. Okay? So let's do the simplest possible case of a tension problem. Well, not the simplest, I guess. Okay, you know what that means? That's ice, okay? This is a hard wooden frictiony surface. This is an ice surface. So mu static equals 0 and mu kinetic equals 0. So that's my way of saying a frictionless surface. So we've got a box on a frictionless surface like this, and we have a rope attached to it, and the rope is like that. And for the rope, the tension equals, did I do numbers? 20 newtons, right? All right. A rope with a scalar tension of 20 newtons is pulling at 30 degrees. What is that going to do? I don't have a mass in here. We're just doing forces. Well, all you do is you say, well, the force is along the rope. There's the tension vector right there. It's along the rope, and it's whatever length is 20 newtons. In your cartoon, it doesn't matter. We don't draw all the vectors perfectly to scale. So if you want to do a free body diagram, unless you're doing this in deep space, you would probably have mg down. And would you still have a normal force? Does ice create a normal force? Well, it's frictionless. Yes, it does. Right. So friction and normal, nothing to do with each other. It'll still create a normal force like that. And then the tension is going to come along and just apply this vector at 30 degrees, or whatever I said it was, like that. So there's your free body diagram. 3 forces, normal, mg, and tension. If it's not moving, do I need to draw a friction force on it? No. Right? If it's not moving, oh no, I would need a friction. Well, this is going to move. Never mind. Is this going to move? Yes. No friction because it's on ice. There's no friction. But if you look at it just visually, you can tell there's nothing canceling the right horizontal tension force. So it's going to pull, right? So it looks like this. Imagine this is a frictionless surface. Look at that demonstration. That's changing your life right there. Yeah. Okay. Now let's calculate how this tension force we're applying is going to change things. Okay. So let's do the F and the Y and the force and the X, and just apply a Newton's second law and see if everything's the same or something different, new, is exciting is happening here. So sum of the forces in the Y equals the mass times the acceleration in the Y. Okay. Of course, it's not moving in the Y because we know we're not going to lift it, or we might. But let's say it only moves in one dimension. Then we would say, okay, let's add up all the forces in the Y. The normal force is up, right? Minus mg is down. And tension, the vertical component of tension, here's my right triangle, the vertical component is sine. Because it's standard, we defined angles the right way. It's t sine theta, and it's up. Sine of 30 degrees in this case. And I'm going to say the problem told you that it's sliding along the ground. It's not being lifted in the air. So we'll say the acceleration up is 0. Okay. So you can already see this has already done something a little bit different, is the normal force is reduced. Right? N is usually just mg, but now it's mg minus t sine of 30 degrees. Right? So normal is reduced. Because you're pulling up on it a little bit. You could also not do it at an angle. I could also reduce the normal force between the table and the block just by pulling like this. And if I pull hard enough, it goes up in the air. But if you pull at an angle, it's the same thing. When I do this, I'm reducing the normal force. If I'm reducing the normal force, what am I also reducing? The friction. Yeah, the static friction is less if I pull up at a high angle. It's more if I pull at a low angle. So actually, it is important. Even the y, which looks pointless, something important happens. You change the normal force. What about the x? Sum of the forces in the x equals mass times acceleration in the x. So in the x, we have t cosine theta going forward. And what do we have pulling it back? Nothing, right? Because it's frictionless. I should have put some friction in this, I guess. And this equals ma. So, you know, the acceleration is just t cosine 30 over m, if we were doing this numerically. Okay. So that's tension. I'm sorry, that's all it is. Let me try to make it more exciting. Oh, so here's like a hard problem that'll cause all kinds of confusion. Let's see. That's not that hard. You want to do the hard problem or talk about the inner ear? Or do we have time to do both? We have time to do both. Okay, let's do this. Okay, so box mass M on a surface mu k. So you got to know what I mean by a surface mu k. Just use your context. What do you think that means? That means a surface where when the box slides on it, the coefficient of kinetic friction is mu k. Okay, I just didn't want to write all that. Right? Pulled at tension T, so the box on a mass M on a surface mu k is pulled at tension T at theta. Okay? So most problems would not be that the opposite of verbose, right? They'll give you more detail and they'll give you a drawing here. So here is the drawing, mass M mu k and tension T at angle theta. Right? And here's the interesting question, is what angle, or what theta gives the maximum A, the maximum acceleration, right? If I have a constant tension I'm going to pull with, I can take that tension and I can pull this way. And you say, well, that would give you the most force in the right direction, but also has the highest friction. Right? I can say, oh, okay, I'll use my tension to cancel some friction. Oh, now there's hardly any friction, but I'm not really pulling it to the right, am I? It's like my accelerating component is gone. So somewhere in between is the right value. Okay? Somewhere in between is the right value. So let's go through it real quick. Some of the forces in the y equals 0. You're given that it's sliding, right? So let's go through the sum of the forces in the y real quick. In the y, oh, we didn't do a free body diagram. Oh my God. M, G, N, T, like that. And then F, kinetic. There's your free body diagram that includes friction. Okay. Let's see. So in the y, we're going to do it the fast way. We're not going to do all the angles in detail. N is up, minus mg is down, right? And then t, it's the sine component, plus t sine theta equals 0. Basically what we just did, because the friction doesn't act in the vertical direction. So we get the normal force, again, is mg minus t sine theta. The normal force reduces, the tension that we're pulling up with reduces the normal force. Right? So now let's look at some of the forces in the x. This is where it gets exciting. Is mass times acceleration. This is the thing we're trying to mess with. We want to know how we can get the maximum A, right? So we say, okay, in the x we have t cosine theta, pulling it to the right. This has no component in the x, no normal force, no weight, but Fk is pulling back, isn't it? Minus F, the kinetic force. And that equals the mass times the acceleration. Okay, so this is new. Now we're getting pulled by tension with friction. Very exciting, okay? Let's fill this out a little bit. We have t cosine theta minus, but what is the friction, kinetic friction? That's the one that's constant, right? We don't have to think about static and varying. It's just mu k times the normal force. But this is the new normal force. Mg minus t sine theta. Mg minus t sine theta equals ma, right? So this tells us the new normal force. This is your new normal. And this tells you the acceleration. Okay? All right. I check the time. Okay, we're cool. That tells you the acceleration. So, but now let's look at the question. So that's kind of like this typical thing I do in lecture, and I say, okay, you're fine now. But then this impossible question comes along. You have to do by yourself. So the question is, what theta gives you the maximum A? Right? So what value of theta is going to maximize that A there if you plugged in a bunch of the numbers? You could do it in your calculator. You'd probably make a little plot, right? That's what you guys would do. I saw somebody nod. I know. Or they have been falling asleep. I don't know. What you would do in terms of calculus, though, you might remember maximizing a function. We would write A as a function of theta. Can you write this function? A is a function of theta to go back to your algebra notation there. Well, you can. You just divide through by that mass, right? So then you have A equals t over m cosine theta. That's just a constant times cosine theta. Minus mu k times g, because the m cancels. All right, that's just a constant. And then plus t over m sine theta. And if you want to find the maximum of a function, what do? You set something equal to something, right? You set the derivative equal to 0. Maybe that phrase sounds familiar. Gives you an AP calculus nightmare. So we're going to say, let's calculate dA d theta in this calculus-based physics course. Okay? What's the derivative of cosine? Negative sine. So this becomes negative t over m sine theta. What's the derivative of mu kg with respect to theta? 0, because it's a constant. As you change theta, does this change? No, it's a constant. Plus a constant, plus 0. The derivative of sine is cosine, plus t over m cosine theta. And to find the maximum of a function, you take the derivative and you set it equal to 0. Like that. Why do I not have a mu anywhere? Oh, I don't need a mu anywhere. Hold on. I dropped a mu, didn't I? Yes, let's see, that mu was supposed to distribute. There we go, mu k. Thanks for having my back. There's supposed to be a mu right there. Okay. And therefore, there's a mu right here. There we go. Okay, so we set it equal to 0, and now we just start canceling things, right? If we set these, it's just these two terms are equal. The tension cancels, the mass cancels, and we have sine theta. It goes to the other side. It makes it positive, equals mu k cosine theta. Well, that's starting to sound familiar. It's basically saying that the tangent of theta is mu k. Okay. So the angle, I'll call it max, theta max. As soon as we set it equal to 0, we were finding a specific angle, theta max, not just any angle. Max, right? So theta max is mu k. So if we want the angle that gives us the maximum acceleration, it's the inverse tangent of mu k. Okay? That's what you need to know. So you'd say, well, the kinetic friction, it's like 0.5. So take the inverse tangent of that, and that's the angle that'll get me the most acceleration. It'll make it move the fastest. Now you might say, well, that almost looks exactly like when we tilted the ramp to measure mu s, doesn't it? It was inverse tangent of mu s. Is this like the same? It's like, no, it's totally just, it's coincidence. They have nothing to do with each other. Right? For the other one, the frictional force was varying as we changed the angle. Here, the friction force is constant. It's totally different equations. It just happens to come out the same. Okay? You might also say, if you're a smarty pants, you might say, how do you know that was a maxima? It could have been a minima. I'll take another derivative and blah, 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 blah. I also happen to know from a close personal friend that if you add sine and cosine, it kind of looks like that. So that original, the first extrema that you see will be a maxima. But it could have been a minima, and then we'd have been screwed. But I wouldn't let that happen. Okay. And then if we wanted to plot this, inverse tangent looks something like this. If we wanted to say, okay, for all the mu k's we could have, what theta max is it going to look like? And it kind of looks like that. So sure enough, the higher mu k, the bigger the friction force, the higher the angle you need to pull, right? Because the bigger the friction force, the more the benefit is to overcome the friction force. Friction force is small, you're better off just pulling like this. Friction force is big, you want to pull like that to get the maximum acceleration. Right? So that's kind of that's an example of a tricky one, just with one part instead of like 5 parts. Okay. Let's see. Let's talk real quick about, let me just tell you what a pulley, okay, one thought problem about a pulley, and then we'll do Newton's third law. Okay, but I got to say one thing about a pulley. Just so you'll know, is that a pulley changes the direction of a rope. A rope, but maintains constant tension. So you will see problems like this. A rope goes over a pulley like that, and here's a mass M. Can you draw it like that? There we go. Now, the rope is turning. It's going around the pulley, and it's attached here solid, and the mass just hangs there. So we could say, what's the tension? Right? The tension, well, to get the tension, do a free body diagram on the mass. Right? And then the mass looks like this. Oh, I don't draw the body. You want to do a free body diagram, I'm sorry. A little dot. Right? mg down, and then tension force up. Because the tension applies a force equal to T wherever it's connected. Right? And it's going to hang straight down, so the tension is straight up. Right? So the tension here, sum of the forces in the y equals 0 because it's static, is tension minus mg equals 0, so tension equals mg. Done. Right? So you'll do lots of problems like that, and the main thing I want you to see when they get more complicated is that the tension remain constant. All the pulley does is change the direction of the tension. Okay? There are more complicated problems. I'll put a couple online. But here is a tricky thought problem before we do Newton's third law. What about this? Here's a table with 2 pulleys and 2 masses hanging, each one hanging under the influence of gravity. Right? Each one pulling at mg. And maybe you can tell I'm going to trick you. Each one is pulling at mg. What's the tension? Think about it for a second. What's the tension? And I'm going to do a 3 count, and everybody's going to say what they think the tension is. 1, 2, 3. 0. I heard 0t and 2t. Okay. The answer's t. It's only t. It's tempting to think that the answer's 2t because there's 2 masses pulling, isn't it? A rope pulls with its tension in 2 places. Okay? This rope pulled with mg here, and it also pulled with mg here. Okay? This rope is pulling with mg here, and it's pulling with mg here. Okay? So sometimes you don't see it in a problem, but the rope is always applying its tension at 2 ends, even if one of the ends just disappears and isn't part of the problem. Okay? You could also get it just by saying, I don't have to think about all this. I'm going to do a free body diagram just on this. It'd be the same process. The tension would have to be mg. If the tension were 2 mg, the 2 things would fly up in the air. It'd have to be a spring or something like that. Okay? Okay, I left us 12 minutes to talk about Newton's third law because it's very important. Okay? We've got to spend some good quality time together on Newton's third law. A couple of problems I didn't get to, I will put online, so you'll have access to them. But, you know, Newton, important guy, came up with 3. We don't want to shortchange him and give him a 67. We want to do all 3 of his laws. Here, let's see. Oh, look at all that. Okay, so Newton's third is also one that you can kind of recite. Wow. I've never seen that much hype over Newton's third law before. This is kind of one that you can just say to yourself. Let's all say it together. For every action, there is an equal, I can write as fast as you can talk, and opposite reaction. See, I told you I could write faster than you can talk. We've all heard that. I heard Newton's second law in a commercial this morning on TV. They actually said it. What commercial? It was something, I don't know, it was like an insurance commercial or something. For every action is equal and opposite reaction, but action was Newton's way of saying force. For every force, there's an equal and opposite force, is really what it means. Okay? So the key is all forces are interactions between 2 things, only 2. Every force we've talked about, I could tell you the 2 things that are interacting. Okay? So we call those action-reaction pairs. The forces are action-reaction pairs. So for example, when the block sat on the table, right, we talk about a normal force up on the block. The block applies a force down on the table. And it has the exact same amount. The normal force up equals mg, the mass of the block times g. The table feels a force equal to mg, the mass of the block, not the mass of the table. When the rope pulls on something, there's a tension force applied here, and there's a force applied to the rope. That's why the rope has tension. Right? It always works out that way. Okay? So let me just get the screen, because there's something you need to be able to see. I'm sure it's going to give me trouble. All right? Because what we're going to do is we're going to demonstrate Newton's third law. Okay? And there's one ultimate best way to demonstrate Newton's third law. That's going to eventually come on. This doesn't recognize me with my glasses on yet. All right, hold on. The best way to demonstrate Newton's third law is with arm wrestling. Okay? So I usually bring down a football player and arm wrestle them. But the football team is in Hawaii. Poor babies, right? So I thought, what glass-jawed punk at Rice could I come up with to arm wrestle? And I have the ultimate Dr. DeNicco. And let's see, he's going to stretch a little. This will eventually be a poll where you can answer the question. What we're going to think about as Newton's third law is whose palm is going to feel the most force once this arm wrestling match is over. And that's what you can vote on if the screen comes up. Okay? Okay, hold on. I'm ready. All right, we're going to get right here. So are you right-handed or left-handed?
I'm right.
Supply to me. Okay, you're righty, I'm lefty. Or you're right?
I'm
okay,
right.
Here we go. Now let's think. Oh, it's not coming up. You got to think about whose palm is feeling the most force. You ready? Go. Ah! He got me. Thank you, Dr. DeNicco. Thank you, Dr. DeNicco. No, the screen didn't come on. That's all right. So think about for a second. I think I can get this to come on. I think I can get this to come on. Y'all can be voting. Just we'll give you 1 minute. Whose palm felt the most force in that brilliant display of masculinity? I'm sorry for the masculinity on horrible display here. Okay, you can't vote. Let's do a virtual, let's shout out the answer, right? So you're either going to shout out DeNicco or Hafner. Whose palm experienced the most force in that arm wrestling match? 1, 2, 3. Same. Oh, you guys are so smart. Damn Rice students. I can't have any fun with you guys. But this is a case where you got to think about Newton's second law, or Newton's third law, right? So I said the palm of your hand, right? So this was DeNicco's palm, and this was my palm. The force between them was the same. But what's weird is the whole thing accelerated. Right? Why did the whole thing accelerate? It's because DeNicco's arm is just a little stronger than my arm. Right? Okay? So the net force on the whole object was not balanced, and that's why the whole thing accelerated this way. But the actual pressure between them, the actual force between them was equal. If I put a spring scale between our hands, it can only have one reading. It's not going to say, well, the force over here is big and the force over here is small. It's a spring scale. It only can press a certain amount. So the force in between is the same, but it's the force of the rest of our bodies that makes the big difference. So the last thing I'll say then about these is when you're asked to find action-reaction pairs, people find it very difficult because they're mixing it up with Newton's second law, N2 and N3, right? So let's think about a quick table that will help you do these problems. Not that we give that many of them. But Newton's second law, how many forces do you deal with in Newton's second law? 0 to infinity, right? In Newton's second law, you're getting the acceleration of an object. It can have as many forces as you want on it, right? In Newton's third law, you're only dealing with 2, right? So this is forces, and this is objects. How many objects are you thinking about in Newton's second law? 1. How many objects are you thinking of Newton's third law? Always 2. When you're asked to find action-reaction pairs, you are not summing the forces on an object. You're thinking about the interaction between 2 objects. What are you calculating when you do Newton's second law? The acceleration, usually, right? You're trying to get the acceleration. What are you calculating when you're doing Newton's third law? Nothing. You're not calculating anything. Why do we do Newton's third law? If it doesn't calculate anything, why do we even bother? Is because we're IDing forces. It helps us ID forces. It helps us find them, and it helps us get their magnitude. Okay? So you have one homework problem where you're thinking about some stacked boxes, right? And I forget what it is. I think it's the boxes are all sliding or something. And you got to think about the forces these boxes are applying to each other. Well, you might be good at calculating, okay, what's the normal force that these apply to this? Okay, well, it's N. Well, you say, well, what's the normal force this applies to this? it's also equal to N. So it's a way to get the magnitudes of all the forces by checking that any two things pushing on each other, it has equal and opposite forces. Okay. Let me just answer these leftover questions and then we can stop. I didn't know how long that would take. I thought I would last longer, but class has to end early. Let's see. Why is the pulley on the right? Here we go. Why is the pulley on the right have mg from the wall if it is in the x direction, not the y? Oh my God, that's such a genius question. Let me make this very clear because you'll be doing a lot of tension problems, so you definitely want to know this. The genius question is, I said, where did it go? Oh my God, did I erase it? It was I think I erased it. It was this. It was we had the wall with the thing on it and going around that, and it had a mass. And we said, why is this force mg? It's not in the right direction. It's not a weight force. It's the tension force pulling that equals mg. It's the tension, and I'm just telling you its magnitude equals mg. And the reason it can go this way is that's what a rope does, is it takes the tension as a scalar quantity and it applies it in whatever direction you want, right, to the things it's attached to. So if I want to apply gravity sideways, I get out a pulley, I string a rope over it, I put a weight here, and I apply gravity sideways. That's what the rope is for. Last one. Why am I rushing? Did you cut your sleeves? Yeah, I cut my sleeves. Where do you think I shop? You know, it's like, yeah. Okay, so I'll see you Tuesday.